Hello everyone. Welcome to the second seminar from BeyondTheEdge. Today we have Eddie. I will make a quick introduction here from Eddie. Eddie completed his PhD at the Vrije Universiteit Amsterdam in 2018 under the supervision of Rink and Bouwe van the Berg. He then spent several years at the University of Urbana-Champaign in Illinois, founded by the Dutch Rubicon grant. After this, he served as a co-principal investigator at FAPESP São Carlos, and then as a Chapman fellow at Imperial College London in UK. He is currently a principal investigator at FAPESP, founded by FAPESP Young Investigator grant. His research interests include network dynamical systems, bifurcation theory, and complex systems, with a principal focus on developing rigorous technique that deals with interaction structure and that are informed by algebraic and combinatorial methods. So thank you, Eddie, and please welcome.
Yeah, so thank you very much for the kind introduction. Thank you for the invitation. So this talk is about cluster synchronization in hypernetworks and how this is a higher order effect. So let me explain all those terms as we go through them. So this is joint work with Bouwe, Rink and Søren van der Gracht, seen here defying gravity on Mount Fuji. So this is work with these guys. So let me start with a bit of motivation. So this talk is about networks and hypernetworks, right? So here's a model that a lot of you have probably seen already. If you haven't, don't worry about it. This is not going to play any role in this talk, at least not in this way. But what you see here is that you have a couple of variables. In this case, if this is really just the classical Kuramoto model, then these take place on a circle. They have some internal dynamics, so they evolve. In this case, they just go around the circle, and then they influence each other by, in this case, so the sign of the difference. So if we see this, when people see this in general, they would often say that this is a network. So a network, because you have three, you want to think about it as three dynamical systems that are then coupled together, and they are coupled together dyadically, meaning that, there's clearly, you only care about the difference of the state with another one, and here the difference of the state of another one. So you can see this as links, two links influencing this node one. Now, in contrast, if you see a model like this, it's maybe hard to say that this is a network, right? Because you have the input from the other nodes, and it's sort of being pooled here. And that's how it's being fed to node one over here. So what people typically do is they think about this as a hypernetwork. And we'll get much more into depth about what I mean by a hypernetwork and in what way it's not a network. But heuristically, people want to think about this as a hypernetwork. That's what you often see in the literature. So then what about this thing over here, which of course it looks a bit big, but at first glance you want to say, well, it's a network because you have here a node and it depends on this difference with node 2 and this difference with node 3, and the function, by which it talks to its environment is a bit more complicated than what you have over here. But, there are still these pairwise things, so this should be a network. But the kicker here is that this system, this third system, is actually exactly the same as the second system, maybe with a factor of 1/2. I didn't check that. So it's a hypernetwork or it's a network. So really, that was the motivation behind this talk, this topic. When do you want to see something as a network? When do you want to see it as a hypernetwork? And if I start with a network, say a class of systems that is seen as a network, and I now start introducing hypernetworks, I sort of jump on that hype train. Am I really introducing something new, or am I just giving a different name for what is secretly just, again, a network? So we saw here that this is that these were in principle all networks, right? So you can summarize all the equations here as just saying, oh, there's a typo here, obviously, by just saying that this is a single response function of some variables coming in. This bar means you can switch it. I will go into much more detail about that bar. It means that you can switch these two variables and the outcome will be the same. But really, you want to think about this as a network. There are just 3 nodes. They have some internal dynamics and they talk to each other. So really the question remains, do we need hypernetworks? Does it give anything new? So what we started doing is we started looking at the network formalism and seeing if we can adapt it to a hypernetwork formalism and see if really something changes. So just as a really quick overview, what you often do if you want to define a class of dynamical systems that somehow captures your network structure, you look at the different nodes and you give them response functions. So corresponding to the right input space and the right output space, I put a circle here. V is some space that corresponds to the circular nodes, and a square, V square, corresponds to the square nodes. You give them some response functions, and then you look at your graph, and then you start writing down the ODE. So in this case, x1 dot, it's a round node, so I give it an F. I just look at everything that comes in, and I plug that in. And these are my equations for x1. And in that same way, I build the entire ODE for the entire network. So a little caveat, something that can happen is in this talk, in this picture, all the arrows are of different types, which I've indicated by all these different colors and all these different frills. But of course, it could be that you have 2 arrows of the same type corresponding to some kind of identical type of input. And then indeed, what you typically do is you put that bar here. So that bar simply means that if I look at this function f, it is symmetric in these 2 variables. If I switch them, the function is the same. The output is always the same. So this is the network side. So what about the hypernetwork formalism that we want to develop, right? So in hypernetworks, you want to think about it not being so obvious that you have dyadic links. So just in every slot having one thing coming in. But like I said, you kind of want to see it as dynamics being, as inputs being pulled and then fed into your node. So this would be sort of a picture example. So we have here 2 hyper edges feeding into node 1. And so what we kind of want to do is we want to write that like this. We want to say that the equations for x1 are some f, some response function of itself. And then you sort of here have those pooled inputs. But of course, these brackets in the middle, they mean absolutely nothing, right? They're now just for capturing that these are somehow pooled. But if I just vary over all f, then these brackets mean absolutely nothing. And this is kind of the problem that we started with, right? Like there is no difference between the network formalism and any hypernetwork formalism, because if we just vary f, that difference is not seen in the different classes of ODEs that you can write down. So is the situation absolutely hopeless? Is there no way of capturing really what it means to be a hypernetwork? Well, here's a situation that becomes where things become slightly different. So now I have again 2 hyper inputs, hyper edges, but they are of the same type. And remember, if you're of the same type, we kind of wanted to have this bar that says it doesn't matter what direction you evaluate them, right? So this is very strongly mimicking the Golubitsky-Stewart et al. Formalism, right? If you're familiar with that. So what we want to do is we want to write down the equations, but now, because the two hyperedges are the same, we want that if we change those triplets, right, we switch them around, the output is the same. And this is really truly different from classical networks. Because what you see here is I'm allowed to take these all three, simultaneously move them to the front, and by extension move these to the back. But that's all I can do. So for instance, I'm not saying that you can, for instance, take these two input nodes and switch them around. Because in general, the way this hyperedge works, the way it pools the variables and feeds it into the equations for x1, it need not be symmetric on the changing x2 and x3. For instance, you couldn't even change 3 and 4 because they're different types of nodes. They might have wildly different inputs. So I'm not saying that this is happening. And of course, by extension, I'm also not saying that I can just take the first nodes of every hypernetwork and change them and leave the same, and leave the rest the same, right? So there's really a different kind of symmetry property of F that we demand in this hypernetwork setting. And it's something that you cannot naturally get if you just have classical dyadic edges. So this is really a new, well, I don't want to call it a phenomenon yet, but it's a new, well, descriptive phenomenon if you go to hyperedges. Of course, now the question becomes, will we actually see something new? And again, do we still have really a different class of ODEs or still not so much? But okay, we have good hopes now, right? That we might be able to find something new in hypernetworks that you do not see in networks, because at least we have now a class of ODEs that has properties that you cannot just capture by making a clever choice of network. So, all right, that was sort of the introduction. Now, we needed to make this precise. So again, this is very much mimicking the network formalism. So we've come up with the hypernetwork formalism. So a hypernetwork for us is a tuple, I want to say quadruple, VH source and target. So V is just the set of vertices, right? A hypernetwork has vertices. H is a set of hyperedges. In general, this will be a generalization. So the hyperedges could be edges, but in general, they're not, right? So given a hyperedge, we can give it a target, right? Where does it lead into, which is a single vertex? And we give it a source, but a source is an ordered list of vertices, right? Because if you recall, they all have one target, but they can have multiple sources. And it matters in what direction I evaluate it. So it has to be an ordered list of source vertices. So that's just what the source and the target do, right? These are just functions from H to V or ordered lists of V. We call this K the order of H. In other words, order 1 hyperedges are just classical dyadic edges. And the maximum of the orders, this is also sort of nice. We call that the order of the hypernetwork, right? So this is just the sort of the most hyperedgy hyperedge and its order. Finally, a little thing you want to put in there to make it a bit more, a bit more engaging is that we give both vertices and edges a type. A type is just, you can think of it as a color, right? So we had, for instance, 2 red hyperedges, but we also had a red and a blue one. And for the vertices, we had round and square, the type nodes of vertices, right? So this is all the information we have. So it's just an equivalence relation, right? And then we need two consistency conditions. And that will just be there to be able to make a nice class of ODEs once we have the definition of a hypernetwork. And they are a bit, you know, they're not too exciting, but again, this is just for consistency. So if you have two hyper-edges of the same type, right? So type is like the color, they have to have the same order. Otherwise, you can't really compare them. And then the targets have to have the same type, and all these sources have to have the same type. So it does not make sense for two hyper-edges to correspond to sort of the same type of input, but lead into wildly different nodes or receive information from wildly different nodes, right? That's just what this captures. And the other thing is essentially the dual notion of this. If you have vertices of the same type, then they have to receive the exact amount, the same number of hyper-edges of the same color. And that's just what's written down here in a bit of a you know, oblique fashion. So in other words, again, it does not make sense to say that two vertices are of the same type if they receive wildly different inputs, right? Wildly different hyper-edge inputs. So this is just all to have some consistency. And this was already there in all the pictures I showed you. So if this is a bit too wordy, you know what's going on here. So if we have a hypernetwork, we can then make, we can then bake a class of ODEs from them, right? So for each vertex type, you choose a phase space. So vertices of the same type, they evolve in the same phase space, and they see their surroundings via the same response function. But then, of course, you want your response function to have the right symmetries with the bars, right? So putting all, so for instance, if these corresponds to two of the same hyperedges, the same type of hyperedge, you want to be able to switch that, which is exactly what we saw all the way at the beginning. So here's an example of such a hypernetwork. I've used slightly different notation in these kinds of hypernetworks. It's a bit annoying if I fill this up completely with some color. So I just do it, I just write it like this, but this is a hyperedge of order 2, right? All 6 of these are of the same type, by the way. Otherwise, I would have given these different colors. So if you look at this, then the corresponding ODE will be, well, the round nodes, they don't actually receive any signals, so they only evolve via their own internal dynamics. But for node 0 and 1, the square ones, which will be y0 and y1, they receive, you know, input from themselves, and also these different angles, brackets corresponding to the different hyperedges, right? So there is again that symmetry that I can take the pairs and switch them around, but I cannot switch around in one pair, and certainly also not take inputs from different pairs and switch them around. But this is the symmetry, right? This is what I mean by the right symmetries that this function f has. So what we're often interested in is generic phenomena, meaning that we allow f to vary over essentially any function, or say any smooth function, with this symmetry properties, with these symmetry properties. So, okay, so far so good. So we have pried out a class of ODEs from these, you know, this very formal definition of a hypernetwork. Well, what can we do with that, right? So at this point of the talk, I'm still going to really mimic what can be done for ordinary dyadic networks. Later, we'll actually see a phenomenon, it's a bit of a spoiler, we'll see a phenomenon that is really different. But for now, we want to be able to compare dynamics across hypernetworks. And to do that, we introduce hypergraph vibrations. So again, the definition is a bit more technical than it needs to be, but we have two hypernetworks. Recall these are tuples, vertices, hyperedges, sources, and targets. And then a hypergraph vibration is just a function that sends vertices to vertices, hyperedges to hyperedges, and it has to preserve the types, right? So you have to send round nodes to round nodes and red hyperedges to red hyperedges. And so at this point, we only have maps between vertices and maps to hyperedges. These, of course, have to play nice. So it sends the unique target vertex of a hypernetwork, of a hyperedge to the target vertex of its image. And likewise for the ordered source vertices, right? So this is just saying we have a map of graphs, but now of hypergraphs, right? So these two maps, they have to play nice, respect sources and targets. And then finally, this is a bit of a technical one, but what you actually want is if you look at a single vertex and you look at its image vertex, then you actually want to have a bijection of the hyperedges coming into the one and the hyperedges coming into the other. This is a bit technical, but when you kind of look at it, you see that there's really nothing going on. I mean, this is easy to check. So here is an example of a hypergraph vibration. I'm sending the square nodes to a single square node, all the round nodes to a single round node, and then there's actually no choice anymore where to send the edges. So this is an example of one of these vibrations. So they're purely on the side of the graphs, right? They're purely on the side of the hypernetworks. But of course, we want to do something with the dynamics. So here's the dynamical side of that definition of a hypergraph vibration. So if you have a hypergraph vibration from some hypergraph to a hypergraph, you can very easily see that you get a linear map from the phase space of one of the hyperedges to the phase space of the other one, but the direction is reversed. So we had a hypergraph vibration from this n to this n prime, and that induces a linear map from the phase space for n prime to that of n. So it's contravariant, right? The arrows now go the other direction. But if you just look at the definition, there's nothing to check here that this is well defined. It's just induced by a renaming, right, of the vertices. Then, of course, the theorem is that if you take admissible vector fields, just so vector fields, right, ODEs, like we defined earlier, for your two hyper networks, of course, using the same choice of response functions, same choice of phase space for the different types of nodes. Then this linear map that we defined here, that's really just sort of, a renaming of coordinates, actually defines a semi-conjugacy between the corresponding ODEs. And I can just write that semi-conjugacy like this because the R are linear maps, right? So it sends solutions of the dynamical system of M prime to solutions of that of F to the admissible vector field for this hypernetwork. And the proof is just squinting your eyes at the definition. Essentially, you note that the definition of a hypergraph was exactly made so that this holds. So here we have this hypergraph vibration. And if you kind of look at it, what it does is the map will just be x, y goes to x, y, y, right? So recall, it goes backwards. It goes from the phase space of this to the phase space of this guy. And then you can actually see that the dynamics of this is then realized as the dynamics of this guy restricted to an invariant subspace. And the invariant subspace is, of course, x1 is x2 is x3, y0 is y1. Sorry, x0 is x1 is x2, y0 is y1. Which, if you set that here, you see that it is indeed an invariant subspace, and you precisely get this system back. So that's just all that's in there. We want to find a graphical way of coming up with these semi-conjugacies. All right, so this naturally leads to the sort of the final concept where everything still kind of works the same, which is that of balanced colorings and synchrony spaces. So very often when you're looking at network dynamical systems, you're interested in these spaces, x1 is x2 is x3, that are invariant under all these systems. So exactly the space like we found here. And the corresponding notion in terms of the graph, the hypernetwork, is that of a balanced partition, which is again shamelessly mimicking the network, the dyadic network story. So what is a balanced partition? It's a partition of the vertices in a hypernetwork such that if you have two nodes, in the same class, they have to have the same vertex type. Remember, like being round or square. And there is this little sort of pesky notion of the hyper edge type, right? So if you have these guys and you look at all the hyper edges coming in, then these hyper edges have to have their sources, be respected in the same way by this partition. I'll give you an example. This is, again, way too of a technical way of stating something that is rather easy. The theorem is, though, that these robust colorings, I called it a balanced partition. I could also call them a robust coloring. I'm using the same word. I'm using two words for the same thing, but these balanced partitions, they correspond exactly to robust polysynchrony spaces, polydiagonal spaces. So in other words, spaces of the form x1 is x2, y2 is y5, that are invariant under every single network ODE that you write down. And they are precisely surjective hypergraph vibrations. So this is why we already saw an example. So this all works very nice. This is just to say that these hypergraph vibrations, they capture these synchrony spaces, these robust polydiagonal spaces. Okay, so everything so far seems to work exactly the same between networks and hypernetworks. On the one hand, that's nice because, it means that the framework is consistent. The framework seems to work, and all the results that you have for these network formalisms, they work for these hypernetwork formalisms. But of course, this is precisely not what we wanted. We wanted to really put our finger on some way in which hypernetworks are different from networks. And so far we haven't yet. All these results are precisely the same for networks as they are for our new formalism of hypernetworks. But now I claim something interesting is going to happen. So here I have on the left our favorite example hypernetwork, and on the right just simply a network. So what have I done is I've cut the 6 hyper edges. I've cut them just into each of them into 2 edges. So here on the right, I just have a dyadic network, just a classical network. There is a bar because the red inputs, they are of the same type. So I need to be able to change them freely. Same for the blue ones. But if you look at if you look at this network, this is just a corresponding class of ODEs for general G and H, and this is just a general class of admissible systems for this hypernetwork. All right, so let me just replicate that for the sake of space. So these are exactly the same ODEs. Now, finally, something strange happens. You can look at the space, the polydiagonal space, which is where y0 is equal to y1. So if you plug that into equations for the right system, then you actually see that it is always flow invariant. Because if I set y0 to y1, the equations for y0 and y1 will not change. So you remain on this subspace. So this is dynamically invariant for any ODE that I have over here, for any choice of G and H. However, you can actually see that it's not invariant for the system on the left. It's a bit hard to see, but if you take the function, the input function to be as such, then you actually see that the equations for y0 and y1 will not be the same. Because remember, this ordering matters. So here I plug in x0, x1, but here it's x1, x0. And because I chose this particular input function, you will see that the equations are not the same. So this polydiagonal space is not in general invariant for systems of this form. Also very strange is that I kind of used a very complicated choice of f to show this, right? So couldn't I have used a simpler one? Actually, no, I couldn't. Because if I just take f to be linear, right? So then this is the most general linear f with these symmetries, right? I have to be able to swap the pairs. Then if I write that out, I get this system. But a general h, if I make it linear, looks exactly the same. So since my given polydiagonal space was invariant for this system, it is invariant for all linear systems in particular. And therefore, because the linear systems are apparently the same, it's also invariant for all linear systems here. And that is really the first smoking gun that something is going on between hypernetworks and networks. So apparently in hypernetworks, looking at the linear response functions alone does not allow you to determine all robust synchrony spaces, right? Just to reiterate, if I choose f and h to be linear, then I just get exactly the same systems. And since I found an invariant, since I found a polydiagonal space, a synchrony space that was invariant for this guy, it has to be invariant for this guy for the linear ones, but it was not invariant in general. And so just looking at the linear terms is not enough to determine all robust synchrony spaces. So I should say at this point, it's a classical theorem that for networks, it is enough to look at the linear systems. You can prove this. So for linear systems in this formalism, for network systems in this formalism, the linear systems do determine all robust synchrony spaces, but apparently this is not true in hypernetworks. And also recall that I had to give a pretty complicated, in particular nonlinear system, third order response function to see that it is not invariant. And indeed, even if I go for quadratic ones, I do not see any difference between these two classes of ODEs. So that led us to come up with an alternative result. So for network systems, looking at linear terms is enough. What we claim is that if you have a hypernetwork system with a given partition, right, that refines the partition into vertex types, and you define the corresponding polydiagonal space, so just space given by some nodes are the same when they're in the same partition class, then the following are actually equivalent. The partition P is balanced. This space is invariant under any admissible map for this hypernetwork. So this I already claimed. But the third equivalent point is that this space is invariant under any polydiagonal admissible map of degree at most k plus 1 divided by 2. So instead of linear now, we actually have the order coming in. And if the order is 1, then this just becomes 1. So we recover the result for networks that there it's enough to look at linear systems. Now, a little bit about the proof. So 1 goes to 2 is trivial almost. You will see that this definition of balanced was made exactly so that the corresponding polydiagonal space is invariant for any inadmissible map. This is really, you notice that that's the construction of balanced. 2 to 3 is even more trivial because if you're invariant under any admissible map, then you're certainly invariant under any admissible map of degree bounded by this. But the hard part is to go from 3 to 1. So to show that if you're invariant under any polynomial system with the given bounds on the degree, then you're in fact balanced. So then you have these nice color properties. So a little bit about the proof. So this is just the hard part. So what would be a strategy to go about it? Well, let's say we want to prove the contrapositive. So we want to show that if P is not balanced, so the colors, they don't work well, then it is not invariant under any polynomial admissible map of the given bound on the degree. So in other words, if it's not balanced, we want to find a polynomial admissible map of the given bound such that it is not an invariant space. And the trick is to use clever choices of monomials. So let me illustrate that, right? So suppose we have some kind of synchrony space. X1 is X2, let's call that A. X3 might be B, X4 might be C. And suppose we have these equations for X1 and X2. So they are, there might be f of some triplet or maybe multiple triplets. And if we plug that in, we get A, B, A, B, C. So this is not balanced because the definition of balanced was that these triplets of A, B's, and C's, they have to be the same if indeed X1 and X2 are in the same class, which they are. So this is not balanced. So we have to find a choice of f with the given bound on the degree, such that we see that this is not an invariant space. So in this case, it's pretty easy, right? We have more A's than we have B's. K is equal to 3, so we're allowed to go all the way up to polynomials of degree 6. But actually for order 3, just take x times y times z. Here you get a squared b, here you get abc. That's in general not the same. So this is not an invariant linear space. So, okay, so we've ruled that out. So maybe that always works. Well, not so fast, because here I have another example. If I now do the exact same one, x, y, z, it's again not balanced because the ordering matters. But if I plug that in, I get the same equations for x1 and x2. So for that particular choice of f, it would be an invariant space. So, okay, we need to come up with another f. Okay, well, let's be a bit bolder. We can go all the way up to order 6. So let's just use x, y squared z to the third. That works very nice because we get c a squared b to the third here. Here we get a b squared c to the third. And, those are not the same expressions. So this is not an invariant space. It's not a flow invariant space if we use this particular choice of input function, of response function. It's still order 6, so we're still good. And this one seems to work very often, right? This is a very good candidate. Alas, take this example now. Take this same response function and we get the same equations again. So this response function does not work universally. Of course, now we could have just taken x and then we see that the space is not in general invariant. So there's always a monomial that works, but it doesn't ever seem to be the same one. So in general, how do you distinguish the following, right? How do you come up with a clever polynomial f such that it distinguishes these guys, such that it shows that this is not invariant? And the trick is that indeed every monomial gives only incomplete information about the number of these terms appearing, right? So because it's not balanced, we know that some of those numbers are different. So we want to find a polynomial that shows that it's not flow invariant, but it's always incomplete information. But together, using induction on sequences with a kind of lexicographic ordering, you can actually get all the information. And that is how you show that if you are not balanced, you can always find a polynomial of the right degree for which it is not an invariant space, right, with the right bound on the degree. So this was really the hardest part of this article, getting our solving this theorem. So it uses some kind of a lexicographic ordering on clever choices of monomials for f. What I also should say is that this bound is optimal in the sense that there are examples such as the one we saw actually. So this is we have a class of examples for every k, and this is it for k is 2. And they tell you that indeed, if you look at all polynomials of order strictly less, you will not be able to find all invariant, all balanced colorings, all invariant synchrony spaces. So for these examples, you really have that the bound is optimal. You really have to look at all polynomial vector fields of order up to and including this order. So this is, of course, why that example was in the background all the time. So, okay, so far so good. So we have really found something in which our class of hypernetworks are different from networks, namely that the linear terms are not enough, the linear vector fields are not enough to get all robust polydiagonal spaces, to find all robust synchrony spaces. So, okay, that's good. But it's a bit algebraic, right? So can we find some dynamical behavior where, as a consequence of this, where it's really different for these hypernetwork systems than it is for these network systems? So can we maybe from this observation on sort of these ghost synchrony spaces, right? Synchrony spaces that you think are there, but then you go to high enough polynomial a degree, and then you see that they were actually not invariant. Can we use that to get some interesting dynamical behavior that you therefore in principle only see in hypernetworks and not in networks, or at least with a high prevalence? And for that, we actually looked at bifurcations of these systems. So we came up with something called reluctant synchrony-breaking bifurcations, and this term will be very clear, once I give you the numerics. So let's go at an example. This is our favorite example, but I've changed a bit what's happening here in the nodes, in the round nodes, right? Some arrows going back and forth and a bunch more self arrows. So if you look at the corresponding ODEs, class of ODEs, it looks like this, just by using the rules that we already did. And I want to look at bifurcation. So recall for a bifurcation, I introduce a bifurcation parameter. I shift it and I see how the dynamics really changes qualitatively. And in my case, just locally, I'm just going to be interested in steady state points. So under some conditions, so if this system has a fixed point at 0, has a steady state point at 0, and if the derivatives have an eigenvalue at 0, then we generically get a steady state bifurcation. This is just standard. You can show with standard techniques you get a steady state bifurcation, but it looks very strange. So what I've plotted here is I've plotted lambda, and I've plotted the coordinates of the stable steady state point. And what you see is that after the bifurcation, they lose synchrony. So they were all the same. They all had the same values. Here they don't. Same for the Y nodes. But the Y nodes, they separate really slowly, as you can see. And this is really a consequence of the fact that Y0 equals Y1 is not actually an invariant space for a system, for a general system of this form. But it is if you look at first order and second order equations. And in fact, if you look at the difference between Y0 and Y1 along this stable branch, and you plot the difference starting from positive, from 0. Oh no, here I'm plotting the same values of lambda. you will see that it very slowly, as in a very high degree, starts separating. So here I've made a log-log plot, and you actually see that it seems to be going as lambda to the power 3. So this is just a fixed slope 3, and in log-log plot, it seems to have that slope. And I should remind you, this is a generic scenario. So for generic choices of f and g, the response functions, satisfying, of course, the right setup for a bifurcation, this always happens, or, always happens. And again, it's really because it starts to notice very slowly that synchrony space y0 is y1 isn't actually there, isn't actually robust. So let me tell you the statement here, the analytical statement. So this is just numerics. So in general, suppose you have a bifurcation in the core. So I call this the core in this class of examples, where it's synchrony breaking, and it does it at lambda to some power. Synchrony breaking meaning all the nodes start doing something different. And they do that in some power of lambda. Typically, this will be power lambda to power 1, but you can come up with examples where it's these are different numbers, as we shall see. So this is just the degree of separation. Define the sum of all these pairwise degrees of separation. Then a bifurcation. So this is the analytical statement that we've proven. Then a bifurcation in this larger system will generically go as the difference between the y nodes going as lambda to the power this sum. And of course, this sum can get pretty big, right? Because you already have 3 terms. You have difference this, and difference this. So it's already a sum of 3, positive numbers. So, and it's a generic phenomena again. So let's go for some more examples, right? If we take this core, you can show that there is a synchrony breaking bifurcation where the difference for all 3 nodes, all 3 differences go to lambda to the power 1/2. So we predict that the y0 and the y1 node go as 3 to the power 2, right? Just 3 over 2, just the sum. And indeed, this is what you see. So here is again the bifurcation picture. First, stable branch is very synchronous, then the stable branch is not synchronous at all. And there is a weird slope there between the y nodes, and indeed, it has a weird kink, and indeed it goes as lambda to the power 3 over 2. Here's another example. Here we have set up the core in such a way that this p bar actually equals 4. So here there are 2 nodes. I think these are nodes 0 and 1 that actually have their difference grow as lambda squared. So the whole sum is 4. And that means that the y nodes, they go very reluctantly. And indeed, they separate with lambda to the power 4 as their leading order. And again, this is a generic phenomenon, which is of course absolutely unheard of for general ODEs, right? And finally, just to drive home that we don't have to do it for 3 nodes in the core. It can be more, can be any number bigger than 3. So here we have it for 4. It looks a bit unseemly, but I hope you agree it's exactly what we had before. And by the sort of design of this core, which is the classical feed-forward network, you actually get that the sum of all those differences is 11 over 4, which is a bit of a wacky number, right? But nevertheless, if you look at the generic bifurcation, you plot the branch, the steady state branch for you plot its y1, y0, take the log-log plot, and it really seems to grow as lambda to the power 11 over 4. And just to drive that home, better than 10 over 4. So just to sort of see that what the resolution is. This is of course no proof, but we have the analytical proof of this. This is just some numerics to drive this home. So now of course the fun game becomes, can you design cores such that this reluctant synchrony breaking has very high or very very wacky numbers. And certainly you can get it arbitrarily high. Getting the numbers is still a bit of a challenge, you know. I don't think I can do 37 over 15. I wouldn't know what chord to choose, but who knows? But this seems to work, and it's all really a consequence of these ghost synchrony spaces, right? So Y0 is Y1 was not actually robust, but it is only if you look at really high order. In this case, only if you look at 6th order degree terms do you see that it is not actually an invariant space for this system. So yeah, so with that, I wanted to finish this talk, maybe just drive home that this is a phenomenon that you can see and even design in hypernetworks. We've seen it once or twice in classical networks, actually in the core of this guy, but I have no idea how to design it. But it seems to be a very natural thing to occur for hypernetwork systems. So they really do seem to be different classes of systems than just classical dyadic networks. So with that, I would like to thank you for your attention. And here are the references.